is what we call directional filter. So if I'm looking at, let's say this is my input, and looking at the first part, this is a coupler. It's a directional coupler. So the input goes in here. So the couple energy go into here, right? And then this one is termination. So I terminate the through. I use the couple, so I lost like 3 dB or 2 dB, right? And the signal go into here, and it's going to couple to this port, and then the through go back in here. So I have a loop like a frequency. So that set up the frequency also is resonating. And then so my input is here, my output is here. Now what does that do if the signal try to go back here? It will see mostly a 50 ohm, the reflections. So we'll terminate it. Some of them try to come back here. When you go back to here, let's see. Go through, go. I need to work out the direction. So the direction would not get on the line. It will not come back to my input. So in other words, this end always see a good match, regardless. Oops. I don't mean that. Okay. The last circuit I want to talk about is we call it a rat race. Not really the last. I have a couple more. So a rat race is this is a microstrip circuit. Everyone is quarter wave, right? So what does it do? People use it as depends on how you want to use it. So just look at the phase consideration again. Okay. So if I have a signal coming in port 1, I'll go to port 2. That's 90 degree, right? Because I have a 90 degree here. Go to port 1 is 90 degrees. So if I go around this way, I have 3/4 plus 1/4. That's one wavelength. Then also is 90 degree, right? Are you with me? So it doesn't matter the signal is going to the left or go to the right, you'll end up at port 2 at 90 degrees. So they end up going to port 2 together at 90 degree, right? No questions? Okay, so how about port 3? Port 3, if I want to send a signal, port 3, this is 180, right? Because it's 2/4 wave. But if I go to the other side, there's one wavelength, 360. So these two are 180 difference. So that means they cancel. That means 0. There's no power go to port 3, right? That's why port 3 is 0. Are we okay? Port 4 is going from 1 to 4. That's 3/4. So that is 270. And this is also 270. That means it's minus 90, right? Minus J plus J 90. Okay. So from the phase considerations, I mean, this is easy to understand. If I send a signal in port 1, port 3 won't get anything. Port 2 and 4 would be equal power split, right? And they would be 180 degree phase shift. So in other words, if this is my input, I will not get any signal here, so might as well terminate it, right? I won't get any signal. So this is 3 dB come out here, 3 dB come out here, but with 180 degree phase shift with respect to this one, right? No question.
I do have a question. Oh, Yeah, I'm still confused about the difference. Why is root 2 times the characteristic impedance chosen?
That is, so a simple explanation is because you want to match the this is 50 ohms, so you want this to be like, oh, instead of 100 ohms, you mean?
Yeah, or yeah, instead of 100 or 50. I know they're parallel, so 100 would be like the intuitive choice.
It's actually because it's not two port. I mean, it's hard for you to, so look at this one, for example, right? You can think of this is 70 ohms, this is 50, so going into it becomes 100. This is 100, so this 200 becomes 50. I mean, I don't think you can look at a 4-port by simply just 2 parallel line, right? That's why I don't want to go into it. To solve for this, you actually have to solve for the matrix to get to the square root 2 to get the impedance here. So right now, just say these are Z1. I'm just going to call it C1, right? And then you have to find out what this impedance will work so that everyone would be matched.
And you can solve for it by multiplying the what's it called?
Oh, the unitary matrix.
Right. Is it called the adjoint?
Adjoint, yeah.
Yeah. Okay. So the adjoint.
S. Yeah.
Right. So that's how you solve for this root 2
yes.
impedance. Okay.
Yes. They work it out. Okay. So now, but I want to point out this. I know it's overtime. If you guys want to go, you can go. But I want to finish this because this is actually very interesting applications. If you think about this, what people use this is
Professor.
Yes.
So you said we're doing HFSS Monday, right?
No, HFSS is your. I'm sorry. Monday is your presentation.
Oh.
If I can squeeze in time, I would try to. I would like to do some, but that part.
You said you're planning to do you're planning to do HFSS early next week.
As soon as you install HFSS, you let me know, and I would maybe hold a workshop before the other guy. So, are you guys all coming to the workshop the ANSYS is putting together? Other than the 2 people are working.
I guess we have to, because we're going to have to know how to use the software.
Oh, good.
The most useful.
It's very useful. I think that's easier than browse through the tutorial yourself.
Is that going to be on Zoom?
It's going to be on Zoom. I'm going to record it, so for the people who miss it, and you can watch it. Okay.
So the challenge is only that the challenge is that we can have our HFS running.
Right. So I'm waiting for you guys to. IT is still resolving that issue. So as soon as I hear anything from them, I would broadcast to you. I'm working with John too. I'm hoping to at least get John going with HFSS, and then he can come out and tell, okay, this is how we're gonna install it. I think that there's still an issue on the license file right now. So, okay. So let me come back to this. This is actually very interesting. Now looking at this, because the signs are different, it's plus or minus, right? Then what people use it is, let me show you. Let's say if I use this as a combiner and the signal is coming in from port 3 and port 1, right? So when I do the combinations, when I go into here, they add up. So at port 2, if I'm looking at port 2, the signal coming from 1 and signal coming from 3, they equal adding, right? So basically, I'm just summing up power from 1 and 3. Yes. But looking at port 4, signals coming from 1 and 3. Looking at port 4, port 1 and port 3 has 180 degree out of phase. So what does that mean? port 4 would get 3 minus 1. The difference of these two signals. So the sum of these two signals would go to port 2. The difference would go to port 4. Right? So a lot of times people use this sum and differences. You split the power, you add back together, you get, you want to get enough power. So the sum would be, you split it and then you combine it. But you also want to look at the difference. A lot of times people compare the two signals and compare the noise, right? So this is where it gives you the noise information.
So you said we're looking at into port 4? No.
Yes.
Coming
so
out.
Port 2 get the sum if I want to add them together. Port 2 get the sum, port 4 get the difference.
That's
right?
based on the last line of the matrix, the last row?
Yeah, because that's S41, S42, S43, S44. So the power going to 4 coming from 1 and coming from 3. They are 180 degrees difference. So when I add them up,
No, go ahead.
When I add them up, that means I'm actually subtracting them, right?
But then port 2 and port 4 both have 0. So there's no power getting delivered to those.
Oh, no. This is S4I. That means the power go to port 4 coming from 1, coming from 3.
Right. So then we subtract.
There's no power coming from 2. That means even if this is not well terminated, I have a reflections coming here, it will not get to my port. And port 4 is 0, that means it's well matched.
So S41, I mean, let's say S41, for instance, does that not mean power going to 1 and coming out of 4?
No, it's power going to 4 coming from 1. 4-1 means going to 4 from 1.
So the output is 4 and the input is 1, right?
That's right.
Okay.
So you could, you were saying something about noise. So you could maybe take a single signal and then split it, feed it to ports 1 and 3, and then combine ports 2 and 4, and then you would get the noise.
Yeah, you can subtract the noise, for example, right? So you probably have heard of like different. I don't know if you have learned any receiving. Yeah, how to cancel noise, right? There's something called like multiple input, multiple output antenna, MIMO. I don't know if you heard of that. People use this kind of concept, or you simply take the signal in and you split it out, and then you look at the noise when you combine them back. I don't. But anyway, I just want to show you that's a very good applications, and AWR simulations, you can play with it, very simple, and try to understand what this means. This is a circuit I show you guys in the transmission line lecture. That's what the red race is. Again, this one is terminated. To terminate, I put a 50 ohms here, but because I don't have it grounded, so I put a quarter wave open stub to make this short, so that becomes a 50 ohms to ground. Right? I mean, so look at this. This is actually pretty useful. The last one is for waveguide. We have something called Magic T. Is a T network. The T network do exactly what the Magic the red race does, pretty much. So again, what people use it is usually let's look at this again. If the input is 1, then the power can go to 2 and 3, right? In phase, equal split. If the power is coming from 4, it will go to 2 and 3, equal split. Actually, I should look at this and this. But 180 degree out of phase. And the reason is 180 degree out of phase, we talked about that earlier. right? It's because of this. E plane, these two automatically get 180-degree phase shift. H plane, they are the same phase shift. Now you put both together, one on top of each other, and that's what the property we get. And so the nice thing about this is, so now you get the same matrix as the rat race. And so what it means is, well, most likely people use this as, this is my input, I'm combining this two. So this is combining together. So the sum go to here, the difference go to this port. Right? Very useful circuit. Right? People use that quite a bit. And it's simple enough and do all the jobs that you need. Okay. So again, try to get a feel of what this S parameter does. You know, by looking at this, can you tell what the function of this device is, and how to use the device, for example. Any questions?
I have a quick question on the previous slide, the one with
Yes.
the actual rat race circuit.
Yes.
Yeah, that one. See that little dark speck, that little dark area right before you get to the fan? Is that the 50 ohms?
Yes. Yes.
Okay.
This is what I was talking about. This type of substrate circuit, it has a layer of resistive layer underneath the gold. So when I etch off the gold, here I etch off the gold and the resistance. Here I only etch off the gold, and so it exposes the resistive layer. So that becomes a resistor.
Okay.
Instead of
just checking.
physically put another resistor there.
I see. Thanks.
What's the purpose of all of the other stuff that's not in the main?
This is to test the resistor, the etching, right? I want to etch it, so sometimes they etch it too long, expose more resistance. So this is supposed to be 50 ohms, and I'm going to test it with an ohm meter. Instead of testing the real circuit, I want to have a test circuit on the side. So if it's not 50 ohms, that means that something's wrong with the etching, right?
In the other squares?
The other square is only mostly for visual. I mean, if they etch it too much, then you don't have the corner connect together or something like that. So when
Is
you
it
look
really gold?
Huh?
Is it really gold? The
Oh, this is gold. Yes, yeah. Very thin layer, 0.7 mils. It's not going to make you rich,
right.
but it's going to cost you a lot of money. People use gold. Do you know why people use gold? Gold is not the best conductor, right? I mean, copper and silver are better conductor. Why do we use gold? We
It's
use gold.
corrosion resistant.
Corrosion resistance. Silver would get oxide too easy, tarnish.
No tin whiskers.
No, yeah, and that too. Oh, you heard about that? Yeah. Okay. Any questions? I know this is a lot of material, but RF is a really big field. I mean, even just do the terminations, it can be one of your design project, right? Just do the flange. Okay. No questions?
I have a quick question for if we're doing the antenna array project. So
Yes.
will we have to use like a couple of these power dividers for splitting the power to each antenna, and then have like a 90-degree phase difference divider for, you know, the circular polarization?
Yes. So instead of using a Wilkinson power divider, you can do a Wilkinson power divider and then have a different line length to give you the 90-degree phase, right? Just another ½ inch or so length. Or you can do one of those branch line coupler that we talked about earlier. That will give you the power split, and at the same time already provide you with a 90-degree phase shift. And then so your lining will be equal length, right? Equal length make it easier for you to lay out. But if you want to look at the radiation pattern, like if I add the 90-degree phase shift or not having the 90-degree phase shift, you want to see how the radiation pattern move, then yeah, do an extra line on the side.
So for 2x1 array antenna, for instance, if we want to connect the power divider, it will matter that we have the same distance between from each antenna, right? Connection
Yes.
from each antenna to the power divider, the distance, I mean, the length has to be the same.
The length has to be the same. Yeah, the distance, yeah, the distance is not as critical, but the length is, right?
Okay.
You can bend the line if it's not convenient. As long as the line length is the same, then you're fine.
Okay.
So I put comments on Canvas after reading your project report. So make sure you read that. I have kind of change or suggest some of the antenna people, because I don't want everybody to do a square patch at 2.4 gigs. That seems to be the favorite choice. So I make sure everyone is doing something different.
Okay.
Any other question? Huh?
Yeah, I was actually going to ask, since there's a bunch of groups doing like square antennas, if since we have to do an introduction next week, I was wondering, I don't know if everyone's here or not, but should we if we could talk about it now or something about how to kind of pick different topics, or do we do that individually, or?
You mean among different groups?
Yeah, because I think there's like 4 groups that are doing like some variations of a 2x2. So I was wondering if we should try to pick what we're gonna do now, so when we go work over the weekends or whatever, we can kind of figure that out. You
can. So I don't need a lot of background. When I say background information, I don't want you to pull out the whole lecture out on phased array antenna. But but if you want to talk about, for example, if you do a 2-to-1, 1x4 or 2x4, did you estimate what the pattern is? Right? So you should be able to at least hand calculate the pattern. I should put an announcement too. You should at least sketch the array pattern, and then you kind of, just like what we did in lecture, go through the exercise. And also, that means you have to define your spacings between the your antenna elements. How far are they apart? Are they quarter wave? Are they 50-degree? I don't know, right? And what is the patterns you expect to look like? And you should, for the antenna people, you should also explore the other software. Is that NEC2, NET2? It's array antenna simulations tools, very easy to use. I think most of the report, the group has used that. So so try to play with that software, and that would help you compare your radiation pattern with what you expected before you do HFSS. Any questions?
Hello, can you hear me? Hello.
Nope. Okay, so
can you guys hear me?
Quiet. Hello? Yeah, you're kind of quiet.
Okay, yeah, I was having a problem today. I was just wondering about the cavity project. How are we supposed, for a rectangular cavity, how are we supposed to determine the coupling or the coaxial connector location? Exactly, because I know there's
so for the cavity project, right, you're talking about,
yes.
The location is totally up to you. So in other words, you have the cavity. Where are you going to put your connector?
But how does that determine which modes are excited? I didn't quite understand that.
You should join the group yesterday. They have a discussion group on it. So the direction of your coaxial pin, the
Yes.
connect, has to line up with the E field
Okay.
inside the cavity. So in other words, wherever you put the connector in the cavity, that's where the E field direction is going to be at. So only those modes that match that direction would be able to populate or be able to pick up. Both connectors has to be matched. So if your connectors are 90 degree, then your modes should have an E field that connect to both. If your connector is end to end, then your E field should be connecting end to end. I don't mean necessarily a straight line connection. I mean, when you look at the field pattern, there should be the E field along the horizontal line. Does that make sense?
Yeah, it does. So you say there's 5 modes that we could say if you had a box, just a metal
Yes.
box, and there's 5 modes you could expect to detect.
Yes.
How would you get 5 modes out of that if they're in line with the E field? I don't see how you'd get 5 modes.
You can get a lot of modes. You can get tons of modes. I only asked you for the first 5 modes. So let me.
Gotta look at the wave harmonics.
Yeah, let me look at the wave. I think it's wave guy. I'm pulling out the field pattern page and look at it again. Okay, let's say this one. So let's say I'm looking at this is the rectangular waveguide patterns, right?
Yeah.
The solid lines are the E field. So let's say if I put a connector on top, just straight down, so like this.
Mm-hmm.
Oh. Like this. So I can excite this mode, right?
Yes.
I can excite. I cannot see. Can I excite this mode?
I wouldn't think so.
You wouldn't, because this is the dashed line. Those are the magnetic field,
Yeah,
the electric field. Yeah, so you cannot pick it up. Can I excite this mode?
Okay, yeah.
Probably not, because
Oh,
if you put at the center, this is 0.
Oh.
If you pick up anything, it's because this is off center, you might be able to see a small peak, but typically not. This is up, this is down, this is 0. So by putting a connector here, you will not be able to pick up a strong signal for this mode.
Okay.
Right? So would I be able to pick up this one?
Yes.
Yeah.
Yeah.
This one, yeah. So you just go through it and say, oh, okay, so these are the mode that I can do. If I do a top and bottom here, then I know not this one.
Actually,
No, not this one. So you just go through, and then you do the calculation and see, okay, these are the type of modes that I can pick up for TE, and then you have to look at TM also, and then say which are the first 5 modes that I would pick up, the lowest 5 frequencies.
TE11 aren't you not able to pick it up there? Because those are just magnetic field lines at the top.
yeah.
Aren't the solid lines curving?
There's no electric
No,
field
this
pointing
is solid
into
line. The E field is here.
But it looks like it's not there at the very center.
It's not there in the very center. Yeah, but I'm not picking up the center. I'm here. Right? My pin doesn't go all the way to the center either. So I'm here. I should be able to pick it up. Just like, can I pick it up from here?
Yes. Yeah.
Yeah, but it also look like 0 here too at the center.
Oh.
Right? But it's curving. It just doesn't go to the center. So if I put a connector, a pair of connector like this, one on top and one on the side, I pick up this one. Would I pick up this one?
No.
No. Will I pick up this one?
Yes. On the
Top
side.
and
that is-
side.
Oh, just the side.
But the top doesn't.
No,
So no.
you wouldn't get it. Okay.
Right. So this one?
You could, yes.
Yes, you could. Right. So there you go. You just walk through the pattern and pick out the first 5. Make sure you do that for TE and TM.
Okay.
I have a quick question. For
Yeah.
TE11, since the electric field's curving to the side, if you have the connector on top and bottom, would it still work?
Yes. Yes.
Okay, all right, thank you.
Yeah. So as long as the connector are along the same direction with the E field at that location, yeah, you don't care how it changes inside.
Another thing, do you consider, so for the first 5, do you consider TE11 and TM11 to be one mode or 2 modes?
TE11 and TM11, or if they are degenerate, 1, because if you only see one peak, right?
You mean
Similar-
one? Okay.
I have a similar question for like, say your A and B are the same values. So TE10 and TE01 would have the same frequency. Do those also count just as 1?
But you might not pick up both. Depends on your location of the connectors.
Okay. If
But,
you say,
but yes, if you do the right angle connectors, then you pick up. Oh, you won't.
what if you connected it at the center, like the face of the picture?
Right. So if you have a square, you still won't, right? So you have a square. If you put a connector here, you excite this mode. But then if you put a connector here, you will not be able to pick up this mode. Right? So it's either you do the TE10, you won't see either one, because if you inject the signal vertical, you will not be able to pick up a horizontal signal. Right? Both connectors have to match the pattern.
So this is for a waveguide. How does it play into the? How is it any different from a cavity in that sense? So,
Cavity, you just add the 3rd dimensions.
okay, the 3rd dimension.
Yeah.
But that doesn't really change it in turn, like.
Not the phase. So here, this is the phase pattern, and this is along the Z directions.
Okay.
So if you want to do this one, you say, okay, I'm going to cut off this tangential is 0, so this is along the Z direction. So I'm going to cut off this, and this length is lambda G over 2 from here to here. And this is my cavity, the first cavity.
Okay.
Right. Tangential is 0, tangential is 0. That's how we cut it.
That doesn't hold true for the circular ones actually. If you because like if you have TM 010 mode, it changes the cross-sectional field.
Yeah, well, because that's right, because that's true. When you have the last one 0, then you cannot look at this pattern. That means the field does not change along the Z direction. Right. That's a special case though. I mean this one. Zero 1 0. That means you're only looking at really. You don't use it as a transmission line, but you're only using this, maybe like this sections. I expand it. So
like straight, only Z direct.
yeah, the E field only straight in
It's
and
like
out.
a capacitor almost.
Yeah, it is a capacitor. It's like a DC capacitor picture. Okay. No questions? All right, I'll see you guys. Yes.
So we want to build a Wilkinson power divider, probably using cheap materials, including, so we'll get some copper strip, like you said. But for a substrate, the substrate has to be a uniform depth, right? It has to have a uniform thickness.
Ideally, yes.
And so where could we find a decent substrate that's readily accessible, like in household materials or something?
Cardboard.
Cardboard is good enough?
Yeah.
So for that, I mean, what do we consider the dielectric to be? Because cardboard.
Air.
Okay.
Yeah, it's just air.
Okay.
But you have to be careful, right? If you press it too hard, then you change the thickness.
Right.
So just be gentle. And if it's off a little bit, it's not the end of the world. So what it means is the impedance of the line change, right? And so when you look at it, it might not be equal power split or but that's okay. For what we do here is okay.
All right. Okay. Thank you.
All right. See you guys next week.
I see.
Let me know if you install HFSS, please.